Lesson 5-1 Rational Numbers, and in this lesson you learn to identify and compare rational numbers and to rename decimals as fractions. Okay, so why is it important? Comparing rational numbers can help you determine which sports team has a better record. Let's take a look at this example in movies. Are you frightened by dinosaurs in movies or amazed by the flight of spaceships in movies? Then you have Jeff Olson to thank. Mr. Olson has created miniature models for many blockbuster movies. Movie makers often use models to simulate situations that would be difficult or impossible to do in real life. To create models, Mr. Olson uses a ratio called a scale. A scale is a comparison of the size of of the model to the size of the real object. So a scale is, if you may want to make it into a ratio, is equal to the size of the model all over the size of the real object. Okay, and also the scale tells how much smaller or larger the model has to be than the real object. Suppose Mr. Olson was building a 15-inch model of a Bigfoot that would be 20 inches tall, 120 inches tall in real life. The scale would be 15 to 120. The model size will be 15 inches tall, and the real life would be 120. If we reduce that to put it in simplest form, it's going to be 1 over 8. That means absolutely everything on the model is 1/8 the size of the same item on the original Bigfoot. Numbers such as 1/8 can be written as fractions. Okay, can be written as fractions are called rational numbers. So here we go. Numbers can be organized into sets. One set is whole numbers. So when you talk about the set of whole numbers, it includes 0, 1, 2, 3, so on and so forth. Okay. It also includes any number that can be written as a whole number, such as 5 over 5, 9 over 1. Okay. Another example would probably be 12 over 2. Okay. Because 12 over 2 is 6, 5 over 5 is 1, 9 over 1 is 9. So those are all whole numbers. Okay. And when you talk about whole numbers, okay, this is our set of whole numbers. Those includes numbers such as 0, 6 over 6, okay, these are all whole numbers, 15, 27, and 9 over 3. These are your set of whole numbers. Another set of numbers is what we call the set of integers. Set of integers includes -2, -1, 0, 1, 2. Notice that all whole numbers are included in the set of whole numbers. Let me define the set of integers for you as well. Set of integers, okay, is the set of whole numbers and their opposites, including 0. Okay, so this is the set of integers, and let's say this is your set of whole numbers right here. Set of integers includes the set of whole numbers. So all whole numbers are integers, but not all integers are whole numbers. Example of integers that are not whole numbers are -8 over 2, which is the same as -4. The opposite of a whole number, which is 4. -6 is an integer. -75, okay. -200. -5 over 1. These are all integers that are not whole numbers. But if you notice, they're opposite of whole numbers. -75 is the opposite of 75. -200 is the opposite of 200. -5 over 1 is the opposite of positive 5. And -4 is opposite of 4. -6 is the opposite of 6. Okay? So we know what whole numbers are. We know what integers are. Let's move on. Okay? Refer to the application in the beginning of the lesson. The model of Bigfoot had a scale of 1 over 8. Both 1 and 8 are integers, but 1/8 is not an integer. Okay, the number system is extended to include numbers like 1 over 8. Numbers like 1 over 8 are called rational numbers, and this is where we define rational numbers. Write this down. Any number that can be expressed in the form of a over b, where a and b are integers, and b is not equal to 0 is called a rational number. Again, b is not equal to 0 is a restriction simply because we don't want a over b to be undefined. Remember the first commandment in math, thou shalt not divide by 0. Okay, if you divide by 0, we make the number undefined. So this is just a restriction. But a and b should be integers. Okay, and it should be expressed in the form of a over b. Okay, so let's define a set of rational numbers. Set of rational numbers includes common fractions such as 1/4. It also includes mixed numbers, decimals, integers, and whole numbers, because all these numbers can be written in the form of a over b. So let's recall. So we have our set of whole numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we know that all whole numbers are also all whole numbers belong to the set of integers. That means all whole numbers are integers, but not all integers are whole numbers. And then we take it one step further, the set of rational numbers. All whole numbers and all integers are rational numbers, but not all, okay? But not all integers and not all whole numbers are rational numbers. Okay, example would be negative 2 over 7. Negative 2 over 7 is a rational number. It can be expressed in the form of a over b, but it's not an integer and it's not a whole number. Okay, 0.5 is another example of a rational number which is not an integer and which is not a whole number. Negative 4 and 1 over 6, another example. Okay, not an integer and a whole number. 3 and 1/3 is another example, okay, of a rational number not being an integer and a whole number. Okay, so you have your set of whole numbers, okay, which belong in the set of integers, and both of them belong under the set of rational numbers. And we define rational number to mean that any number that can be expressed in the form of a over b. Okay. Some decimals are rational numbers. Decimals either terminate, okay, or they go on forever. Okay, so there are two types of decimals that we're going to talk about. The decimal 3.74 is an example of a terminating decimal. Every terminating decimal can be written as a fraction with a denominator of 10, 100, 1000, and so on, and so on. For example, 0.75 is 75 over 100, or 3/4. 1/3 is 1 3/10, or 13. 1.3, I'm sorry, is 1 3/10, or 13 over 10. So terminating decimals are always rational numbers. Now the question is, why are they called terminating decimals? They're called terminating decimals simply for one reason. Let's take a look at 3/4. If I do 3/4, remember 3/4 is the same as 3 divided by 4. And if I make this into a division, okay, 3 divided by 4, 3 goes into the house, 4 goes outside. Okay, 4 is our divisor, 3 is our dividend, decimal of 3 is there. Okay, and then we start dividing. Sorry, that's not a 0. Okay, 0 goes before. There you go. Okay, so how many 4s going to 3? We know that won't happen. So we add a 0. How many 4s going to 30? That's 7. 28. Subtract that. End up with 2. Bring down another 0 from here. How many 4s going to 20? That's 5. 20. 0. It stopped division. The division ends when the remainder is 0. So when the division ends or terminates, that's why we call it a terminating decimal. Okay, that's the name, terminating decimal. Okay, so all terminating decimals are considered to be rational numbers, and all of their denominators are always either 10, 100, 1000, and so on and so forth. Okay, let's take a look at this example. The average adult's fingernails grow to 0.125 inch each month. Write 0.125 as a fraction. Okay, 5 is in the thousands place. So 0.125 is basically 125 over 1,000. Okay, so 125 over 1,000 can be simplified to become 1 over 8. Okay, so the simplest form of, or the fraction form of 0.125 is 1/8. Again, let's recall how we simplify that to become 1/8. Prime factorization of 125 is 5 times 5 times 5. Prime factorization of 1,000. 1,000 is 3 zeros. That means it will have 3 2's and 3 5's as a prime factorization. And simply start cross canceling. That's a 1, that's a 1, 1, 1, 1, 1. And if you notice, it ends up as 1 over 8. Okay? Now we move on to the next type of decimal. Decimals like 0.4444444 dot 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 are called repeating decimals because it is inconvenient to write all of these digits. Okay? You can use bar notation for 0.4, bar notation 4 to indicate that 4 repeats forever. Okay? So 4 repeats forever. Here are other examples of repeating decimals. There you go. These are examples of repeating decimals. In this case, 0.62323 repeat. 0.4613 bar notation 613 means that 613, the digits 613 repeat. Okay? Repeating decimals can also be written as fractions. For example, 0.4 bar notation on 4 is equivalent to 4 over 9. So repeating decimals are also always rational numbers. So when you talk about repeating and terminating decimals, they are part included in the set of rational numbers. Okay? Again, let's find out why it's called a repeating decimal from what we learned last time. Let's find out 1/3 is a repeating decimal. Why is it a repeating decimal? Because if I do division on 1/3, 1 goes into the house and 3 goes out. That looks like a square root sign. Let me fix that. Okay. There you go. Bring up that decimal point. Okay. And then we know that 3 cannot go into 1, so we add a 0. How many 3 is going to 10? That's a 3. Okay. 3 times 3 is 9. We subtract that. We end up with the same dividend we started with. So if you notice, the pattern will continue. That's going to be a 10. That's a 3. That's a 9. Okay. And it will go on forever. Okay. It will not stop. And that's why it's called a repeating decimal. Okay. So when you divide the dividend by its divisor, or when you divide the numerator by its denominator, you will end up with a decimal that repeats forever. Okay? So let's take a look at example number 2 and see how this works. Express each repeating decimal as a fraction or mixed number in simplest form. Okay? In this case, you have 0.5 bar notation 5, meaning that the 5 repeats. There are a few steps in a repeating decimal which we need to take. We need to represent n to be 0.555, which is the repeating decimal of 0.5 bar notation on 5. Okay, and then we take another step. We multiply n by 10, so let 10n be 5.555. Remember, when you multiply 10 by this decimal, you move the decimal 1 space to the right. Thus, you have 5.555 dot 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 means it repeats forever. Okay, multiply each side by 10 because one digit repeats. So the reason why you're multiplying it by 10 only is because you only have one digit that repeats. Okay, so if there are two digits to repeat, okay, what do you think you'll multiply n with? Okay, it'll be 100n. If there are three digits that repeat after the decimal, you multiply it by 1000. Okay, so let's do this first. So after we let n be 0.555 and let 10n be 5.555, okay, we need to subtract, okay, n from 10n to eliminate the repeating part. So we want to get rid of the repeating part, which is this part. Okay, so in order to get rid of that part, we need to subtract n from 10n. Therefore, we have 10n, which is 5.555 dot dot dot. Okay, and then we subtract n, which is the same as 1n, and we know that 10n minus 1n will give us 9n right there. Okay, so this will become 9n, and if you notice, 5 minus 0 is 5. Sorry, that's right, 5 minus 0 is 5, and the repeating decimal disappears. Now you're left with a one-step equation. In order to solve for n, we simply divide both sides by 9, end up with 5 over 9. So 0.5 bar notation on 5 is the same as 5 over 9. Okay, let's take a look at example B. Okay, you have 0.363636, and you notice that the digit 36 repeats. Okay, so this is now 3.36 bar notation on 36. We go back to our first step. We let n be equal to 3.363636. Okay, the original number. Okay, and since two digits repeat, instead of 10n, we multiply 3.36 by 100n. So then 100n equals 336.363636. Why is that? Okay, because we want to get rid again of our repeating digits, and if we only multiply it by 10, it won't get rid of our repeating digits when we subtract them. Okay, so since two digits repeat, we multiply n by 100. Then we do the same thing. We subtract 100n, which is 336.3636 dot dot dot. Subtract n to that, okay, which is 3.3636. You will end up with, okay, 99n equals 333, because 336 minus 3 will give you 333. And if you notice, the repeating digits disappear. Okay, don't mind the line should be here, right there. There you go. Oops, not even straight. Hold on, let me do that again. The line should be here, this way, okay, and not that one. That's a misprint. So it will be 99n equals 333, and then we simply solve for n by dividing both sides by n. If we divide both sides by n, we end up with 333 over 99, or 3 and 4 elevenths. So 3.363636 is equal to 3 and 4 elevenths. Okay? So again, rewind this, pause this, redo example number 2 if you haven't learned it the first time around. The next one, decimals that do not terminate and do not repeat, such as 4.252627, cannot be written as fractions, so they are not considered to be rational numbers. Thus, the set of rational numbers includes whole numbers, integers, fractions, terminating decimals, and decimals. So when you talk about the set of whole numbers, this are rational numbers. This is the set of rational numbers. Okay, so it includes whole numbers, integers, fractions, terminating decimals, and repeating decimals. Numbers such as this one is not considered to be a rational number. We'll soon find out that that particular number is called an irrational number, okay, which we will not cover in this lesson. So we won't concern ourselves with that right now. Okay, so let's take a look at example number 3. Name the set of numbers to which each number belongs. -7 is an integer. Okay? And if it's an integer, it's also a rational number. Okay? -3 and 2/5, it's neither an integer nor a whole number, so it is simply a rational number. 0.545556, okay? Nothing repeats, nothing terminates, continues forever. So this is neither a terminating nor a repeating decimal, so this is not rational. 1.469 terminates, so that means this is a terminating decimal, which also means that this is a rational number. Okay? And like integers, rational numbers can be graphed on a number line. Examples of rational numbers graphed on a number line are shown below. And this is how you graph your rational numbers on a number line. Okay? And we can use that same number line to compare, to choose the greater number from each pair. -2/3 and -1/2. We know that -2/3 is to the left of -1/2. So therefore, in this case, -1/2 is greater than -2/3. In 0.3 and 1/3, we know that 0.3 is 3/10. Okay, therefore we can graph 0.3 and 1/3 on a number line. And since 0.3 is to the left of 1/3, 1/3 is greater than 0.3. And that's the end of our lesson. Thank you for watching.